back. Let's have a look this time at plasmas. This is my plasma globe. And it's doing standard plasma globe things. It's a little bit brighter for you if I touch it like that. So what is going on in the plasma? Let us first of all think of a simple plasma. So let's think of a simple fluorescent tube. So we've got our tube. And we have 4 connections to a standard fluorescent tube, 2 at each end. If it's a straight one or if it's a bent one, they're all at one end. Then we have something in between them, so we are going to apply AC, mains AC, to this plasma tube, and we want it to light a plasma. A plasma is when we have atoms that have lost an electron, so ions, and separate electrons. Those are a bit small for you, sorry about that. So what happens in a normal plasma tube? Well, we have to get this process started, and the tube is typically around about 1 meter long, and so we've got 240 volts, maybe a little bit less, across this tube. Maybe 110 if we're in the US, and that's not very much to strike an arc from one end to another. So in order to light it, we need to do something more clever, and we would like to get some electrons flowing. The easiest way to do that is to heat up some metal, because the problem is, here's my metal, here is the Fermi level here, which is where my conduction electrons are hanging around, and I'm kind of, if this is the negative side and this is the positive side, I'm injecting them in here and taking them out, so I've sort of generated a little bit of tilt in there. Not very much because it's very conductive, it's a metal. If it was a semiconductor I could bend it more. But I have generated this small amount of tilt. However, to get these electrons out, I have to get them to come out to this energy. So if I disconnect this and apply more and more voltage, I can get them to eventually shoot out, but I'm going to need thousands of volts to do that, usually. So to motivate these electrons, one way to help would be to heat them up, and another way to help would be to choose a metal that has a very low work function, which would mean that this height here, to the Fermi level, so let's have it to there, the height above the Fermi level of the top of the metal is comparatively low. It's relatively easy to get electrons to jump out. That would be the case for certain lanthanides, which is why they are used in a whole lot of applications like this. We can also heat it up, and if we heat it up, we are effectively blurring this line. We're making it fatter. If we make this line fatter, the top ones are closer to the top, so we can make it easier for the electrons to leave. Oops, and that's good for our process. So practically, how do we do that? Well, we add a filament here, which is just a coil of wire that's a resistor, so it gets hot. And when it gets hot, the electrons come out, and we add a coil to the other end because it's AC, so we would like it to be symmetrical. And you never noticed that a strip light, or a long one, has a directionality to it, so both ends are the same. We can apply AC to this end, which is fine, but we need to also power these electrodes as well. We need to power the filaments to get them to heat up, and so we need some kind of backup. We need some kind of leak, effectively, to heat them up, and when the lamp is on, when there are already ions in there, we probably don't need to heat them anymore. Typically, the ions and electrons are close by, smacking into the electrode, or filament in this case, are enough to get electrons to come out. So once it's going, we can run it with just this AC, but we need some kind of way to short circuit this effectively so we can heat up the end. So we need some kind of component in here, a thermal switch typically, that will close to allow them to heat up at the beginning and then switch off when the plasma strikes. I'm not so interested in the electronics around the outside. I'm interested in the two processes that are going on. So the first one is electrons are coming out and they're whacking into atoms and knocking out further electrons. So I've got my atom like this, draw a Bohr atom with an electron coming around it, and another electron comes along and shoots the other one out. So we've got now one comes in, two come out. That gives us a positively charged atom, the ion, and that will go towards the negative charged end of the tube, and the negatively charged electron will go to the other end. It's AC, so it's switching, and if we get it long enough, which is why these have to be quite long, we will switch before they reach the end, and then they go back. If we have our tube too short, then they'll reach the end and disappear before we flip our polarity of our AC, and then we'll have a problem because it will go off and then we'll have to heat up the filament again. That's all very well. It's AC, but it's bare, so we've got real AC, we've got real wires going on in there, but do we need AC in there at all? What happens if we apply DC to this? Oops. If we apply DC power to this, our ions will go in this direction, and the electrons will go in the other direction, and the electrons might sustain themselves. So I don't know whether you can see how this is going to work. Ready? The electrons coming along can hit into new atoms, knock a new electron off it, and make a new ion up this end, because this is the positive end, and the new ion has to go all the way down to the other end. The new ion coming along to this end can also, to a certain extent, create new electrons, but it's more likely to do that when it whacks into this filament or electrode at this end. So we could, in this case, make them filaments and apply a really high DC voltage, and then we can rip apart the gas. Typically those are hard to start, so if we do that we will have a problem that I will discuss in a moment. Let me write that down. Pressure. I think I'll do the pressure first. So let's have a look at this. Our negatively charged electrons go in this direction, and the probability that they will hit a neutrally charged atom, so a new one, is dependent upon the pressure and how far they have to go. They are a negative charge moving in an electric field, so they will accelerate at a constant rate, depending on the conductivity of the plasma. If we assume to start with that it's not very conductive, we would expect there to be a voltage drop, like a resistor, across the whole thing. That would give us a uniform field, and in a uniform field this is going to go faster and faster as it gets closer and closer to the electrode. It's not quite as simple as that, but let's start there. That means that our electron and also our ion are going to take a while to get up to a good speed. And let's think about the differences between the two. An electron weighs obviously not very much, and the ion weighs a lot, even if it's a hydrogen ion. A proton weighs a lot more than an electron. And because the force is the same, it's one charge, so we've got force times distance is the amount of energy that we're going to have. We will have the same amount of energy on them, but this ion, the positive ion, will be moving a lot slower, but it will have the same oomph because it was much heavier. That is interesting and useful. It means that the electrons will leave our zone of plasma almost instantly because they will be accelerated extremely quickly. So that's one piece. The other piece is that these other gas particles will define how easy it is for the electron or the cation to get to the electrode without hitting anything. So at very low gas pressure, our plasma will light for some reason. We'll just generate these ions to start with by some process that we're not going to talk about right now, because it depends on what sort of plasma we've got. And they will go to the electrode and just disappear. If we have a very high pressure in there, atmospheric pressure for example, it is very difficult for the ion or the electron to get up enough speed, so it will not be able to get very far, and then it will hit into a new gas molecule and slow down. That's typically what we see in the atmosphere. It's very difficult to get a spark to jump at atmospheric pressure because it is hard for the electrons and ions to get up enough energy so that they can generate a new ion. Then we just have the ions flowing. At an intermediate pressure, it can self-sustain. The electrons can whack into enough gas molecules to generate new ions, new positive ions that go in the other direction, and the ions can whack into the electrode and generate new electrons, and then we have the process continuing. If we don't have that, then the electron goes here and it disappears. There's another issue, of course. If we start it by magic like this, so we've got some kind of process that lights our plasma, then what will typically happen is the electrons will fly very fast out of the plasma zone and make the plasma positively charged effectively compared to everything else. Then the ions will then be attracted to the walls, whatever we've got round, even if there isn't an electrode at the other end. But why have we made a plasma in the first place? Well, in our long fluorescent tube, we will have mercury ions, so we will have mercury atoms, which we will have to first of all evaporate by heating it up. Then they will turn into ions by having electrons knocked off them, and after that they may capture a new electron. So an electron that is hanging around can be captured by this ion, fall through the energy levels and give out a variety of different colours of light. If it's a mercury lamp like that, it's typically ultraviolet light, and so we would have on the surface of our fluorescent tube a fluorescent compound to convert the light into visible light, because we want visible light from those. Or we might want an ultraviolet light, in which case we have a quartz tube to let the ultraviolet light out. If we're going to use it for lighting that we're going to see, we need to block the ultraviolet light from getting out, so we need to use a type of glass that is particularly good at blocking ultraviolet. Then we get to this fellow. This has got two properties that are interesting. The first property that's interesting is that the colour of the little plasma tendrils is not uniform. It's kind of a bluey purple colour in the middle and pink at the ends. That's interesting. Something weird is going on. Another weird thing that's going on is that it's forming tendrils at all, because in my picture it's all full. Why should it form tendrils? Something odd is going on. So we've got tendrils, colour, and a third thing. If we take this apart, we find that this middle piece is glass. So this is a glass bulb, and it goes up and round this strange pointy thing in the middle. If we take the electronics off, there's a wire that goes up the inside of here and touches a piece of dirty looking black stuff. It's some kind of carbon foam that gets in the end and makes a contact. So we've got no contact. In the case of the normal plasma, we would expect there to be an electrode inside and another electrode on the other side. That's obviously useful if we want to pass electricity through a gas. But this is obviously not doing that. It has an advantage that if I touch the outside, because there is no electrical contact to the inside, then I can't get a shock, or not very much of one. It's interesting, one is way more bright than the other one. So where should we start? Let's think about the tendrils to start with. If we recall that in normal atmosphere, if we have an electrical discharge, it would typically be a spark. It's typically a spark because the line along which the air breaks down conducts, and the bit outside does not, because it's air. Because there is a reasonably high pressure, the plasma is really confined to that tube, and if it's lightning, for example, or some kind of multiple strikes, so it's AC, it can still go down the same tube because it takes a little while for the ions to diffuse away. Obviously the electrons can escape very quickly. So if we have AC and a pulse, or we have lightning, which is multiple strikes one after another, so the same as AC effectively, then we can follow the same path, and at higher pressure we can't widen our strike very easily because of the pressure. We can't get enough speed up, and a new thing happens. The new thing that happens is the plasma in the tube is quite conductive. So if we have a plasma tendril, let's just draw it like that, and we've got our two ends of it, then the conductivity along here is very high, and so the charge on the two ends goes down very quickly unless we supply lots of electricity to it. In lightning and in these, there's a very low power electricity, so if we think we can have very high voltage and a very high current if we want to generate high power. If we have a lightning strike, we typically have a high voltage, but not a very high current, or not a massive current. It's enough current to cause a lot of damage, but it's not a huge amount of current. If we have one of these, we have a fairly high voltage, but we have a really, really tiny amount of current, which is why you can touch it and not get injured. If we have a tiny amount of current, okay, there's a little bit of hand waving there, so be careful. If we have a tiny amount of current available to our circuit or our physical system, because we're going to get onto that in a moment with a no contact. Remember, this is a piece of glass here. If we have a small amount of electrons that we can transfer, then we will run out very quickly and the process will stop. If it's an AC process or multiple strikes from lightning, then it starts up again in some way, and then we can have another strike, but these ions are still hanging around here. So that's that. So let's have a think about why the path is so thin. It's thin because if we have more ions, we have effectively more conductivity, and we only need a certain amount of conductivity to move all of the electrons away from our starting point. So if we make this one negative and this one positive to start with, then all of our electrons have gone if we make it this wide, which I've just drawn arbitrarily. Then we've got no more electrons, so there's no more driving force, and so it can't go any further. It's also linked to not having a contact, so let's do that here. So we've got AC on this side, and we've got no connection. We've got a dielectric. So let's have it positive here. If the positive end of our wire is here, that will make the electrons in here move around. And we will tend to move them towards the inside face of our dielectric, which will make this outside face positive. Then a strike will take place, so we will end up with either these ions leaving and floating through space, or the electrons leaving and floating through space and ending up here, causing conductivity. The conductivity is then so high that all of these are used up, and they're just surface ions. So let's get rid of those. Then we've got a negatively charged bulk surface, and if we arrange it well, we can switch our power supply to the negative, and that will push these electrons back up, or it will, yes it will, push these electrons away from this interface and make the other side negative. Obviously this is a little bit more negative than the first cycle, because in the first cycle we only had the ones in the material separating, and now we started off with a sort of negative charge on that part of the surface, and now we've switched it to negative, so now it's more negative. So there are more negatives than there are positive. If we get this right, so the frequency is high enough, the path is still open, there are still ions hanging around in here, and so we can then continue our strike in the other direction. Why is this important? It's important because if we have a dielectric in between, we can't break our surface too much. I can't electrocute myself very easily with this because the electricity has to get through this glass. There's no direct contact either to me or to the gas on either end. And so the amount of current is really, really limited just to the amount of electrons that this glass can spare. Effectively, they've got to go through the glass. So it's only a tiny amount, and it stops very, very quickly. Glass is not a very good conductor, so all it's doing is it's just moving the electrons around inside the material, and the ones that are excess at the surface are the ones that strike. In a lightning strike, obviously, there is much more voltage, and there's much more current. So we've got those two bits. Why are there tendrils, and why can we still have a plasma if there's no contact? We can still have a plasma if there's no contact if it's AC, and depending on what kind of AC, we will either be charging the surface, or we could just move the ions around in space, but that would need a higher frequency again, because then we're not moving the electrons around in our material at the edge, we're moving them in space. This is what would happen if I took this plasma globe and put it in a microwave oven. Then the microwaves would activate the ions directly, or activate the atoms, ionize them directly. Once they're ionized, it will move the ions around. It's quite difficult for a microwave to initiate the ionization process, much more difficult than this, but it's very easy for the microwave to accelerate the ions once it's got them, because that's what a microwave does. So if we have a microwave, we can accelerate the ions. It's a little bit more difficult to start it. So now we come on to the question of why are the tendrils not the same color all the way along. You can see them nicely not being the same color. They're pink and purple. And however, they're pink on both ends and purple in the middle. So we can imagine that something is happening in the middle that's different to the thing that's happening at the ends. The first thing that would come to mind is some kind of ions are being knocked out of the glass, because you can see, if I do it that way around, yeah, you can see if I do it that way around, it's mostly right on the glass surface, if I do it like that. But if I let go of it, you can see there is a bit that extends along the tendril that is still pink. And it has like a little foot that spreads out. So it's something new that's happening. It has a little foot that spreads out because of the process that we had last, that we want to mop up the charge of a patch of surface, so it has to spread out. Otherwise it would be a very tiny amount of charge that it could draw. So it spreads out and kind of sweeps around, so that's why these are moving around. The outside is obviously an open electrode, so it is the one that's causing more trouble. The inside has got the power to it, so it's generating much more electrons and ions. But let's think about what's happening to the conductivity along one of these tendrils. If we have a highly conductive path, then we can imagine that there is going to be something interesting that's going to happen near the electrode, because we've got up to our electrode it's entirely conductive, and then in the plasma it's conductive but not as much. And so we can draw a voltage distribution. So let's have a plus at the top. So this would be our voltage in the electrode, and obviously because it's conductive it's the same all inside the electrode or any point around the back here, and we'll have a negative one at the other end. Typically there's a strong loss of voltage near the surface, and then in the middle there's less of a loss. I'm going to draw that a bit more accentuated. A, because it is more accentuated, and B, because it's easier to see. Like that. Let's do it like that. That looks better. So in the plasma we've got something that's behaving like a resistor, and near the surface we've got something that's behaving like a higher powered resistor, a more resistive surface, bulk, or tendril, depending on the pressure. If we've got a standard resistance, so then we're in the bulk of the plasma. That makes sense. We've got the ions, we've got electrons coming along. So we've got the electrons coming along from one direction, we've got the ions coming along from the other direction, and it's behaving like a steady state. Down near the surface, however, we've got a problem, because in the direction of the surface, near the plus, electrons are going missing. Here the electrons aren't going missing, we're getting electrons from over here, and we're getting ions from the other side, but they can move around in all directions. Here, however, they're being accelerated into the electrode, and that means that there are less charged particles. Likewise, our cations, the ions, the positive ions from the gas, are being repelled from the electrode, and so they're also being pushed away from it. Here, it's not much different. So now we've got nearer the foot, we've got a higher voltage drop, so the speed of our ions is higher, and in the center we've got less of a voltage drop. This is handy for a lot of processes, because the highest speed is going to be near our surface where the ion is going to hit. It is bad, however, if we want to make a light bulb that lasts a long time, because the ions, particularly the ions on this end, the ions are going to whack into it pretty hard. The electrons whack into it pretty hard, but they aren't very heavy. They will heat it up. The ions will tend to knock atoms out, which is one of the reasons why fluorescent bulbs eventually fail. So, what kind of active species can we have in here? Let us take a simple molecule like nitrogen, N triple bond N, and think about what possibilities there are. So we could take the molecule and we could remove an electron from one of the lone pairs and just make it positive. This is an ion that can travel through and it can collect electrons and do stuff. If we excite it more, we could have N double bond N, and we could excite it all the way to get N with some kind of radical cation species. So we can have all kinds of different species, and they can do all kinds of things. So if we have a diatomic gas, we can generate all kinds of different species in there that will do different things. But this has not got complicated things in there like that. This has got argon and another noble gas in there. So it's probably argon and neon. And the argon and neon behave differently in our plasma, because if we apply an electric field, it is easier to extract an electron from an argon atom because the outside electrons are further away. And so those are going to be in this piece, and in our foot at both ends, close to the electrode, there is more energy. There's a higher field, and so the neon is activated both ends. So if we use a mixed gas, we might see a difference. Our plasma gas will determine what color we see, and in this case it's just for fun, but it determines the color along our plasma tendril. The interesting thing about our nitrogen is that we can have a similar effect, but we have different species of the same gas. So we have N2 plus and we have N plus dot in there separately, and they may have different colors. Nitrogen, if you manage to break it into single nitrogens, is red, and normal nitrogen is mostly blue. So it might actually look somewhat similar to this, but we would have to have a lot more power in there to get the nitrogen to break, because we're breaking a triple bond. But moving to our subject, surfaces and surface modification and things, we are interested in how these gases now interact with these surfaces. So we want to know how we can tailor these materials using a plasma. And we have the various things that are in there. So we've got the ions. Let's have an argon plus, which can whack into the surface. We've got reactive ions. Let's have an N plus dot, a reactive nitrogen species, which can whack into the surface. And we have electrons, which can whack into the surface. And we have, what else do we have? We have light, H nu, which can be pretty high energy. We can get far into the ultraviolet with this. There are probably other things, but we'll think about these ones to start with. Yes, depending on the pressure, we can have a new thing that happens. If we're at atmospheric pressure or reasonably high pressure, we can have our ions reacting with each other. So we could have one of these ions, for example, hitting another nitrogen and making a new thing, and the poster child species of that will be O3, or ozone. We can make ozone fairly easily using a plasma discharge, and we will generate a reactive type of oxygen, which is chemically reactive, and it is different to these other species. So let's start with polyethylene. We have polyethylene, and we have ultraviolet light coming along. The ultraviolet light can do things. So we've got that polyethylene chain like this, and the ultraviolet light can cleave the bond, so it can excite the electrons in the bond and cause it to break. So it could, for example, abstract a hydrogen and make a radical on the surface, because we're at low pressure and there's nothing in the gas that is going to take a little while to find a partner. That would be UV. The UV can also break the polymer, or it can cause it to cross-link. So if it hits somewhere in the middle, cleaves off a hydrogen, or it cleaves the backbone, it can rejoin, or it can attack a neighboring polymer chain and cross-link, making the polymer stiffer. This is what happens with aging of polymers if you leave them outside. Electrons are comparatively, well, they will hit our surface, but they're comparatively not very aggressive because they are moving very fast, but they've not got very much mass. The argon ion, which is the next most complicated one, can come in, and that's got more energy because it's heavier, and so it can ballistically knock stuff out that is going to knock off maybe this whole methyl group off the end, leaving a broken bond and causing a similar effect to the UV, but chemically somewhat differently. It can also go into the bulk material, so the ion can shoot into the bulk material, but it has a different depth sensitivity to ultraviolet, which will be absorbed close to the surface, because ultraviolet, if it's short-wave enough, will be absorbed by anything, but it can pass through quite a bit. The argon ions can punch right in to the surface depending on how much voltage we've given them, so what the voltage and pressure are, how much chance we've given it to accelerate. And then the reactive gases can actually react with the surface to add new chemical groups to it. So we would form maybe NH dot, because we've added a nitrogen species and the hydrogen that was on there, so it's squeezed in the bond, but obviously that's going to react further when we get into the air. Ozone likely can do the same, so it can interact with these surfaces, causing them to react, and it can graft an oxygen into a bond, so it can graft an OOH on there, putting the O2 in the middle of a CH bond. That is a peroxide group, and it is now quite reactive. As you can see, we've increased the surface energy by putting all of these things on here, so we can now print on that polyethylene like this. That's typically how you do these. You first of all plasma treat it some way, and then you print. If we take a piece of aluminium, we will have a different effect, because on the aluminium there will be maybe some aluminium oxide, and on the surface of the aluminium oxide there will probably be a little layer of filth. There's always a layer of filth on everything in normal conditions, because we're talking about technical conditions or lab conditions here. If we take something that's been in a normal lab or even a clean room, it will have a thin layer of water on it. And if it's been in a normal area but not a clean room, it will certainly have some greasy molecules on there from bacteria and from humans. It's very difficult to avoid that, so even in clean rooms there's very often some material on there, and that we might want to be getting rid of. It doesn't matter what we do to this, we can get rid of it, so we can heat it up. We will struggle to break water with light, with ultraviolet light, and the ultraviolet light is not going to do very much to aluminium, it's just going to reflect off it, so that is going to do comparatively little. It might cause a reaction of species on the surface, so we might be able to get something to happen, but they're only going to leave if they react with something. If we hit it with electrons, that's only going to make it negatively charged. It's a conductor, and it's got a non-conductor on the surface, maybe, and so very little is going to happen. But if we have these species, particularly ozone and O2 minus, the oxygen anion, whacking into our aluminium surface, that will cause a larger voltage to appear between the aluminium and the outside, like we had last time, and that will cause our aluminium oxide to grow in thickness, but in a different way than we had before. If we have nitrogen ions, we can shoot those in through the aluminium oxide and sometimes implant them into the metal, which will interfere with its crystal structure and maybe make something new. It might make aluminium nitride, or if it's in metals, it might just implant ions below the surface, which change the hardness of the surface layer. So we get different effects depending on what our substrate is. And we might want different effects depending on what we want to do with it. So if we want just the surface to be affected, then we would like to have chemical species, maybe just ozone, and maybe just ions, but not give them too much energy. If we have high energy ions, or we have lots of ultraviolet, we will tend to affect our surface or our material deeper. If we want to add nitrogen functional groups to it, then obviously we don't want any other chemicals in there. If we want to add oxygen functional groups to it, we don't have to worry too much. If we use argon, we can just knock these off and leave radicals on the surface, and when we take it out and expose it to air, it will react with oxygen anyway. So getting hydroxide groups on the surface is usually easy. Getting amide groups on the surface or other nitrogen containing groups is possible, but a little bit fraught, because all of these reactive groups will tend to react with something as soon as we put air back in the chamber. So we may have to leave nitrogen in there for a long time to let it recover. If we want to have fluorine on the surface, we can use a fluorine containing gas. So we can use different plasmas to do different things. If we want to make sure that we don't have ultraviolet light damage, we will have to think of a way to keep the amount of ultraviolet down. If we want to clean our aluminium oxide surface, we will have to think of a way of keeping the energy of the ions down so that we don't knock too much out, because the light is not going to do anything, but the argon ions, for example, if we've got them, if we give them the right conditions, they can remove all of our material. So if we want, for example, a clean aluminium surface with no aluminium oxide on it, we can take it off by shooting it off with argon ions. We do have to be a bit careful, because it causes a lot of damage to the crystals. So you can't just generate a perfect flat aluminium surface with that. You then have to post-treat it in some way to get back, typically by annealing, to heal out all of the problems that you've done and any argon that's inside to let it back out again. If we want to treat with ozone, then we can use a higher pressure, and that will tend to remove some of the other species, so we won't get so many ions floating around. We will get light and ultraviolet, so typically we will have ozone and ultraviolet, and they will affect our surface. We can put a baffle in the way, so we can have a piece of metal in the way, paint it black even, and the ozone can just go around it. Light can't go around corners, so we get different physical ways of separating them. Likewise, if we have a quartz bulb, we can have just the ultraviolet. So we'll leave it there, and we will join next time to talk about how to make different types of plasma and what the differences are.